Hello everyone, welcome to my channel, The Big Boolean Theory. This video is part of a lecture series on operating systems, and currently we are on the second module of this course, that is process management, right? So within this module, we're trying to understand that how does the operating system manage the CPU by providing this abstraction of a process, right? And within this second module, we are currently on the last topic, that is CPU scheduling policy. So within this topic, our goal is to study the different CPU scheduling policies, right? We know that basically this policy or this algorithm, this CPU scheduling policy is used by the scheduler, right, to select the next process that has to be executed on the CPU. And why are we doing all of this? We are doing this so that we can implement the CPU scheduling properly. And once the CPU scheduling is done, basically once it is implemented properly, then we have a mechanism via which we are able to do time sharing. That is, share the CPU time among multiple processes that exist in a system. And this allows us as a user to run way more number of programs on a limited number of CPUs, right? So this is the idea behind a CPU scheduling policy, to select the next process, to select the optimal candidate that can be the candidate here is the process that can be executed on the CPU next, right? So till now, in the previous few videos, we have been looking at the scheduling policy specifically for batch systems. We have said that the scheduling policy is the choice of scheduling policy depends on the goals of the system. So there are different systems like batch systems, interactive systems, real-time systems, and depending on the system, the goals are different. Hence, the algorithms also differ. So we have been studying at the scheduling policies for batch systems. In the previous video, we looked out at our first policy, the very basic policy that is first come first serve, right? So now we'll look at a better policy, an improved policy, that is shortest job first, or SJF, in this video, right? So without further ado, let's get started. So let us start the discussion from this slide. Basically, we are studying the different scheduling policies for batch systems, right? We have talked about batch systems. They basically are a type of computing systems or computers, you could say, where the system accepts a bunch of jobs or a batch of jobs and executes them, right? So there are no users sitting in front of batch systems which demand interactive performance. Batch systems is about a collection of jobs being executed, and in these systems we optimize for throughput, turnaround time, right? We have talked about this in the earlier videos also. So these are some of the algorithms that are used in batch systems. We have already looked at first come first serve, or FCFS, and we saw that although it is simple, it suffers from this drawback that is called as convoy effect, right? And in order to overcome this, we'll look at some better policies, some alternative policies. And in this video, let's look at shortest job first, or SJF. So first of all, let us recall the convoy effect problem that we had in the first come first serve. So let's start with the very first example. This will help us to understand shortest job first, right? So let's take a hypothetical system where there are three processes, P1, P2, and P3, right? These are the arrival times and these are the burst times. Let's just assume that this is in milliseconds, right? So there is process P1 with a burst time of 80 milliseconds, which arrives at 0. Basically, all the processes arrive at the same time at the beginning, right? And P2 has a burst time of 10, and P3 also has a burst time of 10 milliseconds, right? So two assumptions that we always will call out, right? When we are studying these scheduling policies, then there are two basic assumptions. One is that the runtime of each job is known, right? In real-time systems, basically in the computers that we use in our day-to-day life, this assumption does not hold true, right? So that is why when we are studying these scheduling policies, it is very important to call out this very strong assumption that the runtime of each job is known. By understanding these simple policies under this assumption, later on we can develop like more intelligent policies which do not require this assumption. But for starters, when we're studying these basic policies, this is the assumption that we are going to make, that the runtime of each job is known. But in real life, this assumption is not feasible. We cannot know in advance the runtime of the jobs, right? And also another simplifying assumption that we will make while studying these policies is that all the jobs only use the CPU and they do not perform any IO. In reality, the computation, basically the execution of a process, follows a CPU IO burst cycle, right? There is some computation, then there is an IO operation, and there is an alternating of these two. But for simplifying the study of the policies, we'll make this assumption that we are only concerned with the CPU computation. That is, the burst time only includes executing instructions on the CPU, not doing any kind of operation on IO devices. So having cleared this out, called out these assumptions, let's proceed. So we'll go again to the FCFS scheduling policy just to recall the convoy effect problem, and we'll see whether shortest job first can solve that problem. So what happens in the convoy effect problem? Let's study from this example, right? So in this example, you can see that there are three processes, P1, P2, and P3, and all of them have arrived at time zero, right? So our ready queue is basically full. It's not full, basically all the processes have arrived in the ready queue at t is equals to zero, and we are going to follow the FCFS, right? So what will be the scheduling order, right? So we'll make the Gantt chart for this. So as we know, FCFS prioritizes processes which have arrived earlier. It schedules the process in the order of their arrival time, right? But as it happens in this case, the arrival time of each process is zero. Every process just arrived at the same time. So just to like break the tie, we can use this tiebreaker that we will follow the process IDs, right? So P1 will be preferred over P2 and P2 will be preferred over P3. A simple tiebreaker, right? Since the arrival times are same, we can go via this tiebreaker policy that the process ID, the lower process ID will be preferred, right? So what will be the scheduling order? P1, P2, and P3. So this is how the Gantt chart looks like. That is, P1 goes first, then it executes for 80 milliseconds, finishes at 80. Then from 80 to 90, P2 executes for 10 milliseconds, and finally P3 goes at 90 and executes for 10 milliseconds, finishes at 100. So this is the completion times. Let's quickly calculate the turnaround time and the waiting time. That will show us the problem, the underlying problem with this kind of scheduling, that is the convoy effect, right? So the turnaround time can simply be calculated using the simple formula that completion time minus arrival time. So just to quickly recall, turnaround time is the total time spent by any process in the system. And it is like the time from the arrival to the completion, the total time it spends in the system, right? So you can see we are calculating the turnaround time using this completion time and arrival time. And the waiting time can be calculated by subtracting the burst time from the turnaround time. So what is the waiting time? So if you look at the life of a process, then there are two things that it does. Either it will be busy executing instructions on the CPU. That time is accounted for in the burst time. But when it is not executing on the CPU, then it will be waiting for the CPU to be allocated to it. That basically during that time, although it is ready to execute, but it is waiting for the CPU. So the life of a process has two parts. Either it will be executing, which is accounted for in the burst time, or it will be waiting. So that is why the sum of burst time and waiting time is basically turnaround time. So to calculate the waiting time, you can just remove the burst time from the turnaround time, which is the total time spent by the process in the system, right? So the formula for waiting time is turnaround time minus burst time, and this we can calculate here. So let us quickly get the average. So the average turnaround time for the processes is 90, and the average waiting time is 56 milliseconds, 56.67 milliseconds. So here lies the problem. You can see the burst time is for P2 and P3 is 10. For these small jobs, right, you can see a very large, considerably large waiting time as well as turnaround time. So if you look at P2, then it is spending 90 milliseconds in the system, of which it is waiting for 80 milliseconds and just executing for 10, right? So like around the burst time to waiting time ratio is around 1 is to 8, right? 8 parts of its lifetime it is just waiting, only one part of its lifetime it is doing execution. Similarly for P3, it's even worse. Out of 100 milliseconds that it spends in the system, that it spends 90 milliseconds waiting, right? And only 10 seconds on execution. So this is what the convoy effect is about. If there is a larger job, longer job that is scheduled before the shorter jobs, then these shorter jobs have a very high like waiting time, and the overall turnaround time, the overall, I mean, say the average turnaround time of the jobs also deteriorates. So this is the convoy effect problem, where the longer job, it is kind of a convoy, right? We studied about this in the previous video. A longer jobs kind of makes the metrics for the smaller jobs worse. The waiting time increases, the turnaround time increases. And if you're talking about batch systems, the whole goal of a batch system is to have like minimize the average turnaround time of the jobs, minimize the waiting time of the jobs, and have a higher throughput. But this kind of a scheduling does not support that. So this is a problem that we want to solve. So this problem is this is a problem that is associated with first come first serve. Now let us see whether we can solve this problem with an alternative scheduling approach, that is the shortest job first or not. So let us start with the definition of shortest job first. So how does it work? So shortest job first is basically a non-preemptive CPU scheduling algorithm that selects the process with the shortest burst time or execution time for execution next, right? Very simple. Basically, it does what its name says, right? Shortest job first. So first of all, a very important point, it is that it is a non-preemptive algorithm. So basically, this means that once a process has been scheduled for execution, then it will not be interrupted, right? It will be allowed to execute for as long as it wants. Only when that particular process which is executing, it gives up the control of the CPU on its own. This could be because it blocks or it terminates, whatever is the reason. Only when that particular process has given up the control, then some other process will be scheduled, right? So this is the non-preemptive part. And the criteria is that whichever job will be selected, let's say you have a collection of jobs. Basically, let's say the scheduler is making a scheduling decision at any given point, and there are n jobs in the ready queue. Then which job will be picked? Whichever is the shortest job, right? Whichever has the minimum or least burst time. So let us understand this with an example. Let us take the same example in which we saw that FCFS caused a convoy effect, which led to the high waiting time and turnaround time for the smaller jobs, that is P2 and P3. Let's see how does this shortest job first algorithm perform on this particular workload, right? Same workload, same burst times and arrival times. So basically at t is equals to 0, all the processes have arrived in the system, that is P1, P2 and P3. And now at t is equals to 0, we have three processes sitting in the ready queue, and the scheduler has to make a decision. It will be following the shortest job first. So which job will be picked first? As you can see, now we are not unlike FCFS where the decision was made on arrival times. In this case, we will make the decision based on the burst time, right? Whichever is the shortest burst time will allow that particular process to execute on the CPU. As we can see in all these three, P2 has the P2 and P3 both have equal burst times, that is 10 milliseconds, and this P2 and P3 have a burst time which is less than P1, that is 80. So out of P2 and P3, which job should be selected? Again, when there is a tie, let's use this simple rule that whichever process has the like lower process ID, right? Process identifier will pick that process. So in this case, between P2 and P3, P2 has a lower ID, right? So P2 will be selected by the scheduler for execution. P2 and P3 both have minimum least burst time, and out of P2 and P3, P2 has a lower process ID, right? So P2 will go for execution and finish in 10 milliseconds. Next, when P2 finishes, right? So first of all, as we said, this is a non-preemptive policy. So once P2 has started execution, it will continue until it terminates, right? So P2 is done. Only when P2 is done, we will think about scheduling some other process, right? So at t is equals to 10, you can see P2 has left the ready queue. It has terminated. We have P1 and P3 in the ready queue. And out of these two, we have to make a choice. So the scheduler will pick P3 because P3 has a burst time of 10, which is shorter than P1, which has a burst time of 80, right? So very simple, P3 goes next for execution and finishes at t is equals to 20. Finally, the only process that is left in the ready queue, that is P1, will be scheduled and it will finish at 100. So like previous time, let us again calculate the turnaround time and the waiting time. So this is the Gantt chart, and let's calculate the metrics. So you can see we'll follow the same procedure. To calculate turnaround time, we have a simple formula: completion time minus arrival time. So here, since the arrival times are 0, so the turnaround time is the same as the completion time. Similarly, we'll use the same formula again, that is for waiting time. We'll subtract the burst time from the turnaround time, right? So here we have the waiting times, and let us quickly calculate the average turnaround time and the waiting time. So you can see here in this case, the waiting time is much better. In the previous case, the waiting time as well as the turnaround time was much higher, right? So let us compare both of them. So in the FCFS, I'm taking the example that we took in the beginning of the video. Same process, that is P1, P2, P3 arrived at 0. You can see the process, the workload is the same burst times. For the same distribution of process or collection of processes, we are comparing the shortest job first against the FCFS, right? So we can see for FCFS, the average turnaround time was 90 milliseconds, which means that on an average, all the processes spend 90 milliseconds in the system. Compare this with that of the average turnaround time for shortest job first. It's less than half, right? So it is 43.34, which is much better, almost half, right? Against the turnaround time, the average turnaround time for FCFS. Similarly, the waiting time has also dropped by almost 5. Like the waiting time for SJF is 10 milliseconds, where that for FCFS was 56.67. So why is this the case? Because the convoy effect problem has been solved. So let us go back. I'll come back to that analogy. So let us go back in the Gantt chart that we saw. Here you can see in the SJF, the shorter jobs have been scheduled earlier than the longer job. And in case of FCFS, this was the reverse. P1 was scheduled before P2 and P3. And that was the reason why the waiting time or the turnaround time for the shorter jobs was so high, right? Because in FCFS, the P1 got scheduled first, right? The overall waiting time, the overall turnaround time increased a lot, right? But that is not the case. Here we are prioritizing the shorter jobs, and we are scheduling the shorter jobs before the longer jobs, and this helps us to avoid convoy effect, right? So that is why the turnaround time and the waiting time in case of SJF improved a lot, right? So we can see that shortest job first in a way avoids the convoy effect that was being caused in FCFS. So let's come back to this analogy. Let's say understand what is happening here with the analogy of a grocery store, right? So just like we have jobs in the computer system which are waiting for allocation of the CPU, in a grocery store line people have some products in their basket or trolley and they are waiting for the billing to be done, right? So obviously there are some people who have like fewer items, whereas some people who are doing their monthly shopping and they have a full trolley of items. So how does the management of the grocery store handle this? Let's say if they use first come first serve, which is usually the case, then what will happen if someone with the like with someone with a full trolley comes, someone, or if let's say multiple people with trolleys full of supplies come, then people with then people with lesser items will have to wait a lot. Let us just assume in this case, just like the example, all the jobs arrived at the same time. Let's make the same assumption that all the people have come with their supplies to the line at the same time. Some people have lesser items and some people have full trolleys. So which policy will basically minimize the waiting time? So if we follow first come first serve here, since all of them have arrived at the same time, in the case of the process we use the process ID. Whatever is the case, if people with full trolleys are allowed to bill first, then the people with smaller fewer items will be waiting a lot, right? That will kind of lead to unfair treatment or poor customer satisfaction. In this case, when all of them have arrived at the same time, then it is a good idea to follow the shortest job first policy. People which have fewer items, one or two items, they should be allowed to bill first and they will quickly move out of the line. The overall waiting time will be short, right? The overall turnaround time or the overall time that people spend in the queue will be minimized. This will lead to a better user satisfaction. So this is how you can see a shortest job first policy minimizes the overall waiting time and turnaround time. So we can understand this with this analogy, right? So in fact, shortest job first can be theoretically proved that it is an optimal scheduling policy given these conditions. What are the conditions? That we are the goal of the system is to optimize the turnaround time, right? It is only optimal if all of these conditions hold true. That is, for a system where we are trying to optimize turnaround time, it is an optimal policy, right? And what are the other assumptions? The burst time of all the jobs is known. This we already discussed, right? Only when we know the burst times, then we will be able to schedule them in the order of their burst times in the ascending order, right, from smaller to largest. If we do not know the burst time of the jobs, then we will not be able to apply this policy, right? So that is again a very crucial assumption that we make. And finally, another very important assumption is that all the jobs arrive at the same time. Only when all the jobs arrive at the same time, then we kind of have a global knowledge of all the jobs that we are trying to optimize for. We will basically sort them in the increasing order of their burst times and schedule them from smaller to largest, right? So only under these three conditions, that is, we are trying to optimize for turnaround time, trying to make it minimum. The average turnaround time should be minimum. If you know the burst times of all the jobs and if all of them arrive at the same time, then we can theoretically prove that shortest job first is the optimal policy. In one of the further videos, we will actually do the proof, right? In this video, let's just understand with some more examples how shortest job first works. The optimal proof we'll do in a future video, right? Let's take another example, and here I'm trying to see basically here in this example we'll try to see is there any shortcoming of shortest job first, right? Does it really solve the convoy effect problem? And this assumption that we are making that all jobs arrive at the same time, if this is not true, then how does the shortest job first perform, right? So with this second example, let us see all of these. So let us take another example, and here we are trying to see that how does the shortest job first perform when that assumption is not true, that is all the jobs do not arrive at the same time, right? So in the previous example, we saw that all the jobs arrived at time t is equals to 0, but here we have p1, which is the longer job, arriving at t is equals to 0, whereas the shorter jobs p2 and p3 arriving at t is equals to 10. So let us see how does the shortest job first perform in this case, right? So let's again make the Gantt chart, right? And by making the Gantt chart, we will be able to get the completion times and finally calculate the metrics. So at t is equals to 0, we have our first job, that is process P1, right? You can see at t is equals to 0, process P1 arrives and it is in the ready queue. And at this point, the scheduler has to make a decision according to the shortest job first. Since there is only one process, there is not much of a choice. P1 is the only process, right? So P1 will be scheduled on the CPU. At t is equals to 10, we have P2 and P3 also arriving, right? P2 and P3 are shorter jobs. They have a burst time of 10 milliseconds if you compare them with P1, which has a burst time of 80, right? So at t is equals to 10, P2 and P3 have arrived in the system. So now there are three processes in the system, P1, P2, and P3. Again, the scheduler has to make a choice. But since we already know that shortest job first is a non-preemptive scheduling policy, so whichever process has been already scheduled, it will run until it completes. So P1 is already running on the CPU and it has not yet completed. It has a burst time of 80, out of which only 10 has completed. So P2 and P3 have to wait in the ready queue. So P1 will first of all finish its execution, and at t is equals to 80, we will make the next scheduling decision. Right. At t is equals to 80 now, the scheduler again has to make a choice between P2 and P3. Since both of them have the same burst times, right? Like there is no one job that is shorter. We'll again go with the tiebreaker policy that whichever has the shortest or the lower process identifier or the PID, we'll go with that process. So P2 and P3 have both the same burst times, but P2 has a lower PID. So we will first allow the P2 to run. Then at t is equals to 90, P3 is the only job to run. So that will run, right? So this completes the Gantt chart and the scheduling of these three jobs. We have the completion times. Let us now calculate the metrics. So we'll first of all calculate the turnaround time. Again, use the formula completion time minus arrival time, right? So these are the completion turnaround times. That is the total time that each process spends in the system. From the turnaround time, we can subtract the burst time to get the waiting time. So this is the time that the process is waiting for the CPU to be assigned to it, right? So having computed both the turnaround time and the waiting time, let's quickly calculate the average. Again, we can see the turnaround time and the waiting time to have shot up, right? So let's compare this with the previous case where all the jobs had arrived at the same time, and using shortest job first, we had achieved a very appreciable or low turnaround time and waiting time. So this again is a bad number. So why is this the case? Why is it bad? Because you can see that shorter processes P2 and P3 have a very small have a small burst time of 10 milliseconds, but these shorter jobs are like spending around 80 milliseconds in the system, right? More than 80. And they're waiting for 50 on an average, they're waiting for 50 milliseconds for executing 10 milliseconds worth of instructions, right? For doing a job that should take 10 milliseconds, they have to wait for 50 milliseconds on average, and the total time they're spending in the system is around more than 80. So again, this is again a bad number. So why does this happen? Because we again have a convoy effect. So you would say that shortest job first was supposed to solve this problem, but it does not solve it always, right? In the previous case, that was a special distribution, right? The previous case looked something like this, right? We had the same process P1, P2, and P3, the same burst times 80, 10, and 10, but the arrival times was like same. All the processes had arrived at the same time. Now in this case, that in the example number 2 that we saw, same processes were there, but and the burst times was also same, but here the arrival times was different. P2 and P3, the shorter jobs arrived later than P1. So now the problem here is that when P1 arrives earlier, it gets scheduled earlier, and since it's a non-preemptive policy, even if the shorter jobs arrive even by a one unit time later, then they will have to wait. This is what happened. P1 arrived at time t is equals to 0 and it got scheduled, and P2 and P3 arrived later at t is equals to 10. They'll only get to execute when P1 completes, which is not until 80, right? So the shorter jobs again have to wait behind the longer job because the longer job got scheduled earlier. So the problem with shortest job first is that if the longer jobs have been already scheduled, since it's a non-preemptive scheduling policy, right? The shorter jobs will have to wait, right? So if the longer jobs have been scheduled before the shorter jobs arrive, then SJF still suffers from the convoy effect, right? We just saw one example where convoy effect looked like it had been solved, but it was just kind of a special scenario when all the jobs had arrived at the same time. If this is the case, then obviously FCFS might give a convoy effect, but when all jobs arrive at the same time, then it's a guarantee that there will be no convoy effect, right? Then the SJF will be actually optimal, but there is an underlying assumption that all jobs have to arrive at the same time. Then we have a global knowledge of all the jobs. We can just sort them according to their burst times and schedule them from smaller to longer burst times in increasing order. But that is not always the case. The assumption that all jobs will arrive at the same time is not practical. And when it so happens, when the longer jobs arrives earlier, they will get scheduled earlier. And since it's a non-preemptive policy, the shorter jobs which will arrive later will have to wait. And again, the shortest job first algorithm still suffers from the convoy effect, right? We can just compare the numbers between the two cases in example one. So this is example one. When all jobs arrive at the same time, the processes are the same, they have the same burst times, but in this case, example one, all jobs are arriving at the same time. In the second case, in the second example that we saw, the shorter jobs are arriving slightly later, right? And you can see the difference in the metrics. That is, in the second case, when the shorter jobs arrive later and there is a convoy effect, the average turnaround time and the waiting time is much more than the first case, right? So again, shortest job first is optimal only under certain assumptions. That is, we saw that all the jobs have to arrive at the same time, right? That is one assumption that we take under shortest job first, right? So let's come back again to the grocery store example. If there is the case that in the previous example, when we talked about the grocery store, we will talk about the case when all the customers have arrived at the same time. Then what we decided to do, that it is better to let the customers with fewer items get their billing done first, so that, like, on an average, people have to wait less, right? But if it so happens that someone with a full trolley, with a full, like, more items basically arrives first, right? If they arrive first, then basically once their billing has already started, we will not kind of cut short, right? If the billing of the customer has already started, and even if they have even if they have more number of items, even if people waiting behind have only one item, we will not stop the billing because it has already started. This is basically non-preemptive behavior. Once the billing has started, we will continue, like, we will finish the billing, right? The person at the counter will finish the billing, then only proceed to the customers waiting behind the one with the trolley, right? So in this case, you can see, if there is a customer which has more number of things to buy, if they come first and their billing has already started, then we can't do much. People who arrive later, even if they have one thing to buy, they will have to wait because billing is already in progress. So this is how most stores behave. That is, they do not interrupt the billing. It is a non-preemptive behavior, right? So this is the problem that shortest job first still suffers, is that if longer jobs arrive earlier, then the shorter jobs still suffer from convoy effect. But if all the jobs arrive at the same time, then it is optimal, right? So in summary, what are the pros and cons of shortest job first? The pro is that it is an optimal algorithm, it is an optimal scheduling policy. If the goal of the system is to optimize turnaround time, first of all, when we talk about optimality, we have to be clear about what are we trying to optimize for. We are trying to optimize for minimum turnaround time, minimum waiting time, right? So if that is the case, then yes, shortest job first is optimal, given that the job lengths are known and all jobs arrive at the same time. The second point is important because only when you know the job length, then we will be able to schedule or sort them, right? In order to apply, whether it is FCFS or shortest job first, you have to know the job length, right? Once the job length is known, we will sort them according to the job length and then schedule. And only when all jobs arrive at the same time, this global sorting or scheduling is possible. If longer jobs already arrive and shortest jobs arrive later, then again it still suffers from convoy effect, as we saw in the example number 2. Both FCFS and SJF suffer from convoy effect. Only when all jobs arrive at the same time, shortest job first is actually an optimal policy. We will look at the proof also in one of the later videos. So this was about the advantages and disadvantages of shortest job first. So this was it for this video. In this video, we saw how the shortest job policy works. We saw two examples. One in the where all jobs arrived at the same time. We saw that there the shortest job first actually did very good. It solved the convoy effect problem for that particular case. But we also saw that if longer jobs arrive earlier and they get scheduled, then due to the non-preemptive nature of the algorithm, the shorter jobs have to wait. So it still suffers from convoy effect. So we are not still there yet. We again need a policy which can help us to solve the convoy effect. We need to look at alternative policies. That is where we'll look at the next policy in the next video, that is shortest remaining time first, right? So guys, this was it for this video. Thank you very much for watching. I'll see you in the next video. Thank you.